So now Camilo de las Heras will talk about the D2 branes with world volume and background fluxes as duals of M2 branes. So please go ahead, Camilo.
Okay, good evening. First, I would like to say thank you very much for the organizers to allow me to give this talk. This work was done in collaboration with Professor María Pilar García Moral at Universidad of Antofagasta. She is my advisor at my PhD thesis done in the same institution. And this work is based on a preprint that we just put on archive a couple of days ago and on another work that we expect to put on the web on the next month. So the outline of this talk is first to give a short and brief motivation of why are we interested in these kind of topics. Then I will schematize some points of non-trivial M2 branes, some points of non-trivial D2 branes. I will mention what is the relation between these two objects, and I will finalize my talk with some conclusions about what we have speak so far. So the brief motivation, it is known that there are 5 known superstring consistent superstring theories in 10 dimensions. They were thought at the beginning that they were independent, but in the second revolution of superstring at the means of the 90s, the community found that these theories were not independent, but they were related through dualities, all right? In particular, S-duality and T-duality. This fact that these 5 unknown superstring theories in 10 dimensions are related through dualities allow the community to think that they are different limits of a single theory in 11 dimensions that it is known as M theory, right? Fundamental objects of M theory are several, but we will focus in our talk on M2 branes. And in 10 dimensions, we are in general interest on string bound states, in particular of bound state of fundamental string with DP branes and the possible restrictions that 11-dimensional theory may imply on lower dimensional theories or even lower effective theories. So non-trivial M2 branes, first, before I mention this, I would like to say that it is known that with Lucian and Nicolai, they found that M2 branes have a continuous spectra. So after this work, the community abandoned the idea to think of M2 brane as a fundamental object of M theory. Toroidal compactification does not improve the spectral behavior of the theory, but in the 90s, a special sector of the theory was defined by Martín Restucia and Torrealba by the imposition of a topological restriction that allows that the theory share a nice spectral behavior. I mean, if we consider a background in 11 dimensions where we have 2 dimensions toroidally compactified, the other 9 dimensions are Minkowski in the Lighton gauge, and we consider that the embedded maps from the world volume onto the compact sector are given by this XR, where sigma, it is a Riemann surface of genus 1 that is related to the spatial directions of the world volume, right? So if we choose this, we have that these are the winding conditions on the maps, the embedding maps onto the compact and the non-compact sector. And the central charge condition can be understood as a non-trivial flux condition over a 2-form well-defined on sigma. And this central charge condition, the name, it is because it is the same term that appears as a central charge term in the superalgebra of the theory. It can be seen that this condition implies the existence of a non-trivial U1 principal bundle over the world volume of supermembrane theory, and it can be geometrically interpreted as the irreducible winding of M2 brane around the compact directions. It was found that this supermembrane restricted with this topological restriction has a discrete spectrum in this work. Therefore, M2 brane with central charge may be understood as it is describing microscopical degrees of freedom of at least a sector of M theory. M2 brane with central charge Hamiltonian is given by this expression that we have here, where there are 2 kinetical terms. We have a potential that is quartic, quartic term. We have a symplectic derivative that it's given by this definition that we have here, and we have a symplectic curvature that appears on the theory restricted with this topological restriction, where this A shall be a symplectic connection, and there is a monopole term, all right, related to this M2 brane and the supersymmetric terms. This theory, it is constrained to some, it has some constraints related with the residual symmetry that the theory has, that it is area preserving diffeomorphism, which in 2 dimensions are symplectomorphism, and this is the local and the global constraint related to this symmetry. Well, so this is the Hamiltonian of a non-trivial sector of M theory. We found in this work that there is another non-trivial sector that can be understood as an M2 brane on M9 times T2, but with a C plus minus flux on the background. I mean, we are considering that this component of supergravity tree form, it's non-zero but constant, and we can define a well-defined 2 form on the target space in such a way that flux condition on it implies a flux condition on the world volume, and we show in this work that the Hamiltonian in such a case is given by this expression, which the only difference with the last Hamiltonian that I showed, it is this term that may be relevant if we have compactified dimensions. In the case that we have flux C minus, this theory is exactly equivalent to M2 brane with central charge. In the case that we have flux related to the component C plus, we have that this theory is equivalent to M2 brane with central charge, with a shift on the spectrum. So this theory is another non-trivial sector with discrete spectrum, and more recently we have found a third sector of M2 brane theory which also has a flux condition, but now we are considering a coupling with a more general background, because we are considering more components of supergravity tree form as non-zero but constant. So in this case, the Hamiltonian is given by this expression that we have here, where the novelty, it is these 2 contributions in the kinetical terms related to components of the supergravity tree form. In this case that I'm showing here, Cm and Cr are given by this expression that we have here, C plus minus are given by this, M and N are indexed that run upon the transverse directions, and R runs over the compact directions. In the last Hamiltonian, you saw a momentum that has a little hat. This hat, what it means, it is that we have performed a canonical transformation in order to eliminate non-physical degrees of freedom that other way are present in the Hamiltonian. In fact, this was a problem that was noticed by the Witt, Peters, and Plewka in the context of M2 branes. We solve it in the context of M2 branes, and we use it to solve the same situation in the context of D2 branes too. So far we have 3 sectors of M2 brane theory, which are non-trivial sectors because they have discrete spectrum. In fact, in this work, we showed that these 2 sectors are equivalent. In the more general case, there is a shift in the Hamiltonian, a constant shift. And we will show in this work that will appear the next month that this new sector, non-trivial sector of M2 brane theory is equivalent to M2 brane with fluxes. Therefore, it is a sector which non-trivial with a discrete spectrum, right? So in this work, we noticed that there are the area preserving diffeomorphism imply the existence of some gauge symmetries in this theory. In particular, there is a symplectic gauge symmetry that was reported in the literature, but there are some new non-trivial U1 symmetries that may be related to the world volume of M2 brane, in the sense that area preserving diffeomorphism allows the definition of non-trivial connections that transform as U1, non-trivial U1 connections on their symplectomorphism. So this is an interesting point of study for our group. So if we now perform, we have 3 different non-trivial sectors of M2 brane theory, we may now think in the dualization process proposed by Dove and Townsend in the 90s, where they say that M2 brane compactified in a background circular compactified, it is dual to a D2 brane. So if we follow this same dualization process that was known in the 90s to our non-trivial M2 branes, what we found it is If we select the Hamiltonian of M2 brane with central charge and perform the dualization, we obtain this new Hamiltonian where it appears two new terms characteristic of Dirac-Born-Infeld Hamiltonian, but we have a symplectic curvature, a monopole term, and a symplectic derivative that appears in this D2 brane, has a new feature, I would say. And we also notice that the diffeomorphism constraint, these are Lagrange multiplier, A0 and lambda. So this constraint, it is area preserving diffeomorphism, and it appears a new constraint related to the U1 symmetry characteristic of the world volume of D2 brane. If we perform the dualization to the other sector, M2 brane with fluxes, we have almost the same Hamiltonian, but with a new contribution related to the dualization of the three form of 11 dimensions, right? And we also have here the appearance of the same features that I just mentioned. And in the third case, in the case that we have the more general non-trivial M2 brane, and we perform the dualization, we have this expression that we have here, where now the generalized metric contains the symmetric part, and the antisymmetric part contains contributions from the Nevessoir sectors, all right, which is constant. I will remember that. So these two terms are related to the Nevessoir's constant flux condition. Well, so far we have three sectors of M2 brane with discrete spectrum. We have performed dualizations, and we have found three D2 brane, three theories that are dual to non-trivial M2 branes. So our question is, which D2 branes are those? I mean, which flux conditions shall I impose to a D2 brane in order to obtain these three theories that I just mentioned can be understood as duals of M2 brane theory, but with some symplectic curvature and on the world volume, and non-trivial U1 symmetries on the world volume. Well, in order to answer this, we will notice that light-cone gauge formulation of Dirac-Born-Infeld was given by Manbeljan, Melik, and this author, where they did not consider the gauge sector. In general, they do not consider the coupling with background fields, all right? They consider Nevessoir 0. So in that case, the light-cone gauge Hamiltonian that they just found is this Hamiltonian where there is a kinetical term, the symmetric part of the generalized metric. It has the same form as in M2 brane, and it appears the two terms characteristic of Dirac-Born-Infeld formulation. The constraints are, as usual, area preserving diffeomorphism and the Gauss constraint. We have just generalized this formalism in order to introduce the coupling with background fields, and this was not done so far because there is a problem with the introduction of non-physical degrees of freedom in the Hamiltonian that we have solved in the M2 brane context. So has the Guessumino term, it has the same form in 11 dimensions, has in 10 dimensions. The solution that we found in last year in order to obtain a light-cone gauge formulation of M2 brane coupling to a constant background without non-physical degrees of freedom may be applied in the context of D2 brane. So we found this is the light-cone gauge Hamiltonian coupled to background Ramon and Nevessoir background fields, and subject to the same constraints as before. So we only notice the appearance of this new term as before, and this contribution in the kinetical term. And of course, this G, it is not the BI, it has a contribution of the Nevessoir field. Sorry?
3 minutes.
3 minutes, all right, thank you very much. So we have imposed some non-trivial, I mean, we have the same D2 brane that I just proposed. We will propose it in a background with two directions toroidally compactified, and we will impose non-trivial flux conditions on two forms well-defined in the torus of the target space that are written in terms of the Ramon and Nevessoir components respectively. So it can be shown that if we perform an identification of the coordinates of the torus of the target space with the embedding maps, these two flux condition implies flux condition on the world volume, and the Hamiltonian that we obtain is this Hamiltonian that we have here. What we notice, it is that this Hamiltonian that it was obtained as a Dirac-Born-Infeld Hamiltonian coupled to Ramon and Nevessoir constant background with fluxes, it is equivalent, it is the same Hamiltonian that we obtained as the dual of a CM2 brane with fluxes. In the case where before the imposition of the flux, we turn off the Neves-Suar background field and we only have flux condition on the Ramon background field, we have that this is the Hamiltonian, and we obtain that this D2 brane with this flux condition, it is equivalent to the dual of M2 brane with fluxes. And in the case that we have a central charge condition on D2 brane, what it is the same to say as a C- flux condition on the torus of the target space, we show that in that case, D2 brane, it is equivalent to the dual of M2 brane with central charge. So far, we found 3 non-trivial sectors of M2 brane theory. We found their duals, but we named their duals in terms of D2 branes with certain world volume and background fluxes, right? So just to end, I want to say that these D2 branes have a symplectic gauge symmetry that was not noticed before, and there are several non-trivial U1 gauge symmetries that we are characterizing on the theory, and that they will be expressed in this work that it is just to appear. Symmetries related to the background field. So just to end, conclusions: M2 brane with central charge, M2 brane with fluxes, and CM2 brane with fluxes are 3 non-trivial but equivalent sectors of M2 brane theory with discrete spectrum. Area preserving diffeomorphism on M2 branes and D2 branes with non-trivial fluxes produce non-trivial U1 gauge symmetries and symplectic symmetries. Light cone gauge formulation of D2 branes with background fields may be obtained inspired in M2 brane light cone gauge formulation. And D2 branes with world volume and background fluxes may be understood as duals of non-trivial sectors of M2 brane theory. Just to end this talk, I would like to say that this work was financed by CONICET, a national scholarship from Chile, Project Fondesit Regular, Semillero de Investigación of Universidad de Antofagasta, Network NT8 of the ICTP, and Project ANT 1756 from Universidad of Antofagasta. Thank you very much.